Swayam Prabha. Digital India. Educated India.
Welcome. So, we are in module 4 where we will learn how to do finite element formulation for Euler-Bernoulli's beam. So, in this lecture we will mainly discuss about beam formulation. So, first I will briefly touch upon the mechanics associated with beam, especially the Euler-Bernoulli beam, and then we will construct weak form, and then finally we will proceed towards beam shape functions, or which is based on Hermite polynomial, contrary to what we have used for the Lagrange polynomial for the bar. Now, let us start with the beam formulation or beam equation, what we have studied probably in first year mechanics or later days. So, the beam, especially the Euler-Bernoulli beam, Euler-Bernoulli beam. So, this is there is some speciality about this beam theory, or that we all know. Suppose there is a beam which is, I am just drawing it in 2 dimension, it may be section may be there. So, so let us say this beam is along this axis is the center line of the beam, or the sometimes we say it is a undeformed neutral axis if the cross section is perfectly square or rectangle. And then this is the x axis. So, and let us assume that the y axis is downwards. So, this is my y axis. So, under the action of load, maybe UDL or some any point load or any other load, the beam deforms. So, the deformed configuration of the beam, if I draw at any point or a particular cross section, particular portion of the beam. So, this is the my deformed configuration of the beam, and this is the deformed neutral axis of the beam. So, this is the deformed neutral axis. So, what Euler-Bernoulli beam suggests that what was perpendicular the fiber, what was perpendicular in the undeformed configuration, it will remain perpendicular after deformation. So, that means this angle between this does not change. So, this is the basic assumption. So, what we have studied in first year mechanics, that plane sections remain plane before and after bending, and this is obviously this beam deflects in the downwards or the along the vertical position, means vertical position up and down it can go. So, now if I write my displacement components, usual displacement components, and the perpendicular axis is z axis of this blackboard. So, now if I write my Vx, that is V is if I write it's a function of x, y and z, then Vx is Wx is the displacement. So what it says is that downward displacement is essentially independent of the y and z coordinate. So it's a function of x. And then the axial deformation, basically u x, y, z is minus of y dw dx. So dw dx is the slope. So w is this w, dw by dx. If you look from here, that at y equals to 0, basically there is no axial deformation. So from where it comes the inextensibility of the neutral axis of the beam. So this is the basic assumption, and then obviously the w or the z axis is there is 0 displacement. Now here if you assume this kinematic assumption, then what we get is the strains. So strain components are epsilon xx, that is your du dx. So naturally this becomes du dx. So this is minus y dw d2w by dx2. So this is nothing but the curvature. So now other strain components, essentially epsilon yy will be 0 because v is not a function of y at all. So epsilon yy will be 0 and other strain components will be 0. The interesting part is epsilon xy, this is also 0. So if you take the du dy and then take dv dx, then this will be so epsilon xy, or if I write the 2 epsilon xy, which is gamma xy, so if I write that, then this is nothing but du d y plus dv dx. So this is nothing but your minus dw dx and plus dv dx is dw dx. So this becomes 0. So you see that there is no shear strain in this beam. So the interesting question is how shear stress is generated, or rather shear force generated. So that's an interesting question here. So that you may look into. And then the potential energy of the beam, if the beam is loaded with some kind of force, which need not be an UDL, I am just assuming an UDL. So the potential energy of the beam is nothing but integral b by 2. So b is the width of the beam. So in this direction the width is b. So now this is integral 0 to minus h by 2 to plus h by 2 is the cross section. This is minus h by 2 and this is plus h by 2, and then this is nothing but your you have to integrate over 0 to L. If I consider the beam length is 0 to L, then the potential strain energy becomes sigma xx and epsilon xx dx, and then the load contribution of the load. So if I take if I integrate over this, then I can just simply write q0 or qx wx. So that's my potential energy of the beam. So if I just simplify it, then probably you are familiar with this expression, that is EI by 2, the B h cube by 12 will come, and this will lead to a moment of inertia, and this will lead to 0 to L d2w by dx2 whole square dx. So then this will be 0 to L Qx then Wx dx. So this is my potential energy, and by taking the first variation, if I in the lecture module 2 we have discussed this, then we essentially do the governing equation. We find out the governing equation of the beam, which is a fourth order differential equation. So that is essentially d2 w dx2. So ei d2w dx2, that is d2 dx2 is actually the q0 or q whatever you say. So if I take q0 is constant, then this is q0. So this is the governing equation of the beam, where x runs from 0 to L and associated boundary condition. So what will be the boundary condition for this beam? So this is a fourth order differential equation. So obviously we need 4 boundary conditions for an unique solution. So at simple boundary conditions we can consider, so at x equals to 0 or L, any one slope or moment or displacement or shear force can be given. So either moment, that is ei d2w by dx2, or slope, that is dw dx, should be given. This is one boundary condition, and another boundary condition is ddx of ei d2 w dx2 should be given. This is nothing but the shear force, or the w has to be given. So this is applicable for 2 points, that is 0 and L. So that will generate my 4 boundary conditions. Now this is one important thing from here. We can observe that shear force and displacements are conjugate pairs. So slope and the moments are the conjugate pair. So either slope or moment has to be specified, or displacement or the shear force has to be specified. Now moment expressions we all know, that is moment is m of x, that is at any section we can compute the moment, that is minus b by 2 to plus b by 2. So minus h by 2 to plus h by 2. So I can just write it even this, and then this is y sigma xx dy dz. I can do this, and this is the moment quantity. So this will lead to my ei d2w dx2. So here I have so this contains one minus. So here I have one of the important thing one need to know, that what is the stresses. So we know all strains. So if we assume the plane stress assumption, so then sigma xx is only the non-zero stress, which is minus ey into your d2w by dx2. So this is my sigma xx, and all other stresses are 0. So now this is the overall theory that we are looking to approximate with the finite element method. Now we all know that this is how to compute the weak form for this type of differential equation. But before I go into directly to that, let me show you the another way, and why we should not do that or what we should not do this. So if you look this equation, then the beam equation sometimes actually I can write the beam equation, that is EI d2w dx2 is my mx, so minus mx. So now this equation with a boundary condition on displacement I can also discretize with finite element method, but this is not a standard practice because there is some problem with this that we'll see. So if I take any Lagrange polynomial and which let us consider some simple beam problem. Suppose this is a simply supported beam and there is an UDL. So this is my UDL. So now this is Q0. Now this beam contains E, I and L is the length, and then what is the boundary condition? Then this is W equals to 0 at this point and W equals to 0 at this point. So this is a second order equation. We need only two boundary condition, contrary to the fourth order differential equation which involves the load. So this doesn't involve the load, rather it involves the moment. So if I know the moment expression of the beam, then I can use this. So this is the first restriction, and naturally for knowing a moment expression for a complicated structure is not possible. So this equation, if I construct the weak form, then this is nothing but the second order differential equation, and we can just use that standard theory that we have learned for bar element. So the weak form, if I choose V is my weight function, then the weak form looks like this. So integral 0 to L dw dx or dv dx into EI and then dw dx into dx, and then this is the forcing term will come into picture. So now this forcing term we can write this. So if I put minus here, and then this forcing term is my plus. So integral 0 to L, if I know moment expression, then this is my weak form or the forcing term, and then there will be a boundary condition associated with. So this boundary condition will be Vx and EI dw dx, something like this. So this is the boundary condition at x equals to 0 to x equals to L. So this is the something we'll observe. So for the weak form to be discretized, to discretize the weak form, we can always use some linear or quadratic Lagrange polynomial and then discretize with respect to W, and then W can be simply like W of x can be phi 1 W1 and phi 2 W2, something like this we can use, and then that is we use a two-noded linear element where only the vertical displacements is in the picture. And then the interesting thing is that that if you compute the dw dx, so this is a linear function. So this is, let me write it for this thing, x by LE W1 plus x by LE W2. So if I consider my dw dx, so that is my W2 minus W1 by LE. So this is my slope, which violates actually the Euler-Bernoulli theory. So this because it requires the slope continuity. So that means at these 2 points slope has to be continuous. So if I just draw my slopes here, so from one element slope could be this, from another element slope could be this. So there is a jump in it. So this jump is violating the Euler-Bernoulli theory. So this is because of this we cannot use this type of this thing, but this can be again higher order polynomial also involve this. So the order of continuity will be reduced. Now if I may show you in picture that how this looks like. So this is just simply I have done it. So because Wx is C0 continuous at the internal element boundary, and then slope discontinuity which will happen, so which is a C inverse continuity or C minus 1 continuity. So this is the problem, and now so this doesn't allow the Euler-Bernoulli theory, and so we generally don't do beam formulation with this. Now sometimes we may argue from that that instead of only slope, why not instead of displacement, why not displacement also can be interpolated in terms of linear polynomial like Lagrange polynomial. So this is also possible certainly, but Euler-Bernoulli theory requires that the slope should be the first derivative of the displacement, which is not required thing for the your for instance Timoshenko beam theory or the deep beam theory that we will be discussing later. So so this is not the correct approach. So we understand this. So what will be the correct approach? So to do that, let us see the weak form of this fourth order differential equation that will be doing. So integral statement, obviously if I choose the weight function Vx, then weighted integral statement is 0 to L Vx into d2 dx2 ei d2w dx2 minus q0 dx. So this is the weighted integral statement, or this is also a weighted residual statement if we choose W is an approximated solution of original W. So now this is a fourth order equation. So we have to do 2 times integration by parts, and if I do that 2 times integration by parts, then it will look like this, that is 0 to L d2v dx2 and then ei d2w dx2 dx. So this will generate my beam stiffness matrix, and then integral 0 to L q0 vx dx. So this will also generate my body force term, and then I will have 2 boundary conditions, which are first one will be Vx into ddx of ei d2w dx2. This is the first thing. So this has to be evaluated at x equals to 0 and x equals to L, and there will be another thing, so which will be dv dx into ei d2w dx2. So moment and slope, this is also at x equals to 0 and x equals to L. So now if you look carefully, that our weak form requires second order continuity at least, because what I mean by that is that we need non-zero derivatives, second order non-zero derivatives for our approximations. So this is one of the thing, and another thing is that our we are constrained with one of the thing, that is W must be or the slope or that is theta slope should be dw dx. So that is the requirement for the Euler-Bernoulli beam theory. So we have to consider theta as an independent variable here. So to do that, we need an element. So let us first plan the element. So let us consider a two-node beam element. So and let us draw the this thing. So this is my degrees of freedom. So this is my degrees of freedom. So this is nothing but W1, W2, and then this is theta 1 and theta 2. So this is my node number 1 and node number 2. Now in addition to these, this is my primary variables. So I need an interpolation function which can approximately interpolate these variables or these values at the nodes. So that is one of the primary requirement, and this because it is not only the W or the displacement has to be interpolated at the node, but the theta or the slope has to be interpolated at the node. This is one of the major requirement of the beam element, where if I use my Lagrange type of polynomial which cannot fulfill the second criteria, that is the derivative of the field variable has to be is interpolated at the nodes. So this is my requirement. Now the secondary variables, which are moments and shear force. So if I consider this, so this is my shear force, and now if I consider these moments, so let us use the that notation that we have used. So this is nothing but Q1. So this is nothing but your shear force at this point. So Q1, let us say that is dW ddx of EI dW dx. So these are the secondary variables or derived quantity. From the primary variables, that is slope and displacements, and then this is my Q3, which is I am assuming that Q3 is negative. This is just for ease of this equation. So you can choose any of the sign convention that you would like. So this is dW dx 2, and now there is a moment so associated with it. So let us denote it with Q2, and this is my Q4. So Q2 is my this thing. If I write it Q2, so this is nothing but EI d2W dx2, and then Q4 I'm just writing it negative, so d2W EI d2W dx2. So this is my moments. So now if I substitute these notations in this equation, then how my weak form will look like. So my weak form will look like this. So this is my 0 to L d2 v dx2 EI d2 W by dx2 dx minus this is my 0 to L Q0 Vx into dx. So this is my the stiffness term, this is my body force term, and the boundary conditions term. So I will just put the boundary condition terms. So at x equals to L, which is LE basically here, if I choose the length of the element is LE, then if I take x equals to 0 and this is x equals to LE, then this becomes x equals to LE. So now the boundary terms will come, so which will be minus Vx and ddx of EI d2w dx2 at x equals to LE and or L. Let us write L, then after discretization, putting the discretization, I'll write in terms of LE. Then the next term will be your Vx and then EI d2w d2w by dx2 at x equals to 0, and then this term will also come. Similarly, this is dv dx. So let us take dv dx minus, this is also again this thing, and then this term, that is EI d2w dx2 x equals to L, and then minus of minus dv dx. So here what we have assumed is my slope is the negative of the displacements. So this is x equals to 0. So now if I write it properly, so this term is essentially my Q1. So this is my Q1, this is my Q2. So I will have these things. So after discretization, and this is Q3 and Q4, so and so on. So the objective is, if I discretize, I substituting by the shape functions or the beam shape functions, what I will get something like this, that is Ke, which will be coming from here. So that is the shape function stiffness matrix, and then I will have the variables. So let me say UE. So UE I will define, and then this will be equals to my Fe. Fe, this will coming from the body force, and then there will be QE will be your this boundary term or boundary reaction terms. Look, this requires us actually, if you remember the bar problem which we discussed in the previous lecture, that the interpolating nature of the slope is very important here, because these quantities has to vanish, or this quantity has to vanish at the other nodes. That means that at other nodes, when I compute at a particular node, and suppose in node 1, then these shape functions associated with, that is the dv dx shape function associated with this, has to vanish at this node. So this is the one of the major requirement that is required in beam shape functions. So this is nothing but we have a 4 degrees of freedom. So naturally my stiffness matrix will be 4 cross 4, and this will be 4 cross 1, and this will be 4 cross 1, and this will be 4 cross 1. So this is standard model that we have discussed in the in case of a bar. Now before I directly go to the shape functions, so what is our requirement? Let me put it properly again. So we need an interpolation for the slope as well as displacement, which we cannot have from the Lagrange polynomial. standard Lagrange polynomial. So if I, for instance, if I have a 4 boundary conditions, that is, for instance, here UE is actually my W1 theta 1, W2 theta 2, and so on. So where theta 1 is minus dw dx, and theta 2 is my this is at x equals to 0, and this is my dw dx at x equals to L. So now these quantities I need interpolation, which I cannot get it from the Lagrange polynomial. For instance, there are 4 conditions for the way we derived the Lagrange polynomial in the previous class or previous lecture. Same way we will be deriving it here, but only thing is that I will now consider these 4 boundary conditions. Now if I have 4 boundary conditions, and if I want to construct a Lagrange polynomial, then the best approximation will be something like this, which is cubic polynomial, or a cubic polynomial, something like this: C0 C1x plus C2 x square plus C3 x cube. So that will lead to my 4 nodes at least. So this will give me 4 constants. So I will have only interpolation about W, not the because this condition I cannot invoke here in case of a Lagrange polynomial. But in case of a beam shape functions, this is a requirement, because we need interpolation of the beam shape functions. And why this interpolation is required? Because you see, one of the reason is here that this has to cancel, and then for the other nodes, so or it has to represent the degrees of freedom at a particular node. So now so this is cubic Lagrange polynomial, so which doesn't assure me that the slope or the first derivative will be interpolating. So and continuous, obviously. So so this is the main requirement, and to satisfy these criteria, this is a new we cannot use a Lagrange interpolation function, rather we will use a Hermite interpolation function. So the Hermite interpolation function. So what will be the Hermite interpolation function? The Hermite interpolation function is very means the approximation is pretty similar, but only the construction is different. So this is also known as the cubic spine function. So this is if I write my Wx with this same this thing, but the boundary conditions that I'll be using will be different. So now C2x square plus C3 x cube. So now my u of suppose let us consider a 0 to LE element. So this is 0 and this is my LE, and then I have 2 degrees of freedom per node. First one is the displacement, and second one is the slope or the derivative of the displacement. So naturally I'm just writing W1. So W1 is just C0 because x equals to 0, and then W2 or U2 which is theta 1. So theta 1 is essentially your minus dw dx. So dw dx is C1, so minus of C1. So now similarly W2, which is C0 plus C1 LE plus C2 LE square plus C3 LE cube, and theta 2 is minus dw dx, at x equals to, this was at x equals to 0 and this was at x equals to LE. So this is, if I do this, then this is nothing but minus C1 minus 2 C2 LE minus 3 C3 LE square. So this is my thing. While in deriving the Lagrange polynomial, we were not using these conditions. So we had a primary variable at the nodal point. So in case of this polynomial, I had to do with a 4 node this thing, so that I can have W1, W2, W3, W4. So which does not assure me that derivative will be continuous, and in fact derivative will not be continuous. So where we meet the derivative of the primary variable is also interpolating, this type of function or safe function is known as the Hermite polynomial. So this is the basic of beam shape functions. So we'll continue with this in the next class. So let us stop here. So we'll continue with the next class. Thank you.